Magnetic motor starters. A motor starter will consist of a contactor and an overload relay. What on earth is a contactor? Well, a contactor is extremely similar to a relay, as in we have magnetic forces that are going to cause the articulation or movement of a set of mechanical linkages which are connected to electrical contacts. But how is that different from a relay? Because a contactor really is going to do the same thing. Well, its primary difference is this. Here's a basic relay, got an electromagnetic coil, it's fixed, and the entire flux path of all of the electromagnetic flux is not going to change. The flux path remains the same through the entire duration of this relay's operation. What's going to set a relay apart from a contactor is that a relay has a relatively low magnetic attractive force, and that attractive force limits the size of the armature here, and thereby the size of the control contacts that we would see, or the power contacts, so the size of the load. Another difference is that the armature movement in a relay has no effect on the magnetic path of the coil, and the significance of that is that there is no effect on the current drawn by the electromagnetic coil with the movement of the armature. So this will differ a little bit with a contactor. Let's take a look at a contactor then. There's a contactor. It's got same sort of thing of line and load connections. We've got movable contacts, and this is just a different form of visualizing it. We have some springs to allow for dampening of the force as this gets pushed up in a vertical direction. This is the moving assembly, and inside there is this portion that connects to the other side of the core, so that the core actually moves a little bit. Now we also have something called a magnetic shading coil, coil terminals, stationary electromagnet. So let's see what the differences are. There is a high magnetic attractive force that a contactor is able to generate. And that's because the magnetic force is being imposed in two places, here and here. So it can move a substantially larger mechanical linkage system than what a relay could. But due to this, the armature movement has an effect on the magnetic path of the coil. And the significance of that is that the movement of the armature has an effect on the current drawn by that electromagnetic coil. So let's take a look at some standard contactor parts. I'm going to show you a real one first, and then after that we'll take a look at some good close-ups of real types of contactors. So let's take a look. We've got this here. There's a standard contactor. You may have seen these in the past before. There are typically line connections and load connections. The line connections are usually indicated with an L, L1, L2, L3, and the load connections are indicated with a T, T1, T2, T3. Whole bunch of information on the nameplate here, but I want to show you the contacts. So inside here you can see there appears to be a bit of a plate there, and this moves up and down. Now you can't really see it from the physical representation we have here, the physical object, but notice that there are some itty-bitty little springs in there. And those springs, the purpose of them is to absorb some of the shock as I pull the armature in. And all that's happening when I do pull the armature in is this. This is a full bar all the way across. When it pulls in, it simply connects the top portion here to the bottom portion down there. So it's called a double make and break. Now, what else is interesting about a contactor versus a typical relay is that a contactor is typically manufactured in such a way that I can replace the coil. So let's see what's in here. This is a part of the core. Notice it's in two pieces. I have one piece in my hand here, and it's got this funny little ring around the edge. And then the other part of it is actually inside. And the other part is connected to the contacts on the top. So this moves in and out. And because it is such a large surface area, there is magnetic attraction here, here, and here, 3 places. And so what that means is that this can pull in a much larger mechanical arrangement of contacts. But we get ahead of ourselves. I said we can replace the coil. So this is the electromagnetic coil. The coil is the item that we energize to produce electromagnetic flux. And so a coil will always have 2 terminals, always. Typically they're labeled A1 and A2, but this is by no means a standard for every single contactor. You can't see it here because my camera is a bit fuzzy, but the contact or the label for your coil should indicate the voltage and the frequency, or if it's possibly a DC coil. So this is it. That's all it is. And it sits inside here so that it is energizing around the coil or around the core. The other side, this portion of my core remains inside the unit. And again, what's happening with the operation is when I energize the coil, this remains stationary, but the magnetic flux produced by it moves the whole assembly up like this, or down, depending on how you want to look at it. Glass half empty, half full. I don't really care about glasses. I'm more of a pint guy myself. So it moves up and down. So there are springs in here that are going to dampen the force, because remember, this is going to happen really quick. Boom, like that. And so you don't want those contacts bouncing at all. And that's what these springs will do. The other spring is actually inside the unit. Kind of hard to see, but it's right in there. And this is what keeps the armature in its present position, which is open. So, interesting takeaway. What you can do is have a contactor like this and replace the coil for whatever voltage you required. Let's say we required 24 volts. Okay, well, most of these items will be sold with 120 volt AC, so perhaps it's cheaper for me to buy the whole thing and then just buy a replacement coil for the type of control voltage that I have available. So kind of an interesting application. Let's go back to the presentation and take a look at some actual parts in a little bit closer view. So here are the contacts that we looked at and the little spring in there. And then the armature, remember that was the moving portion. We had the other springs that kept the armature in place. And then we had the core, the other half of the core, and then the coil, right? The coil, this one's a little bit different. It's a figure 8 arrangement. Loads of different types of arrangements. So this down here stays stationary while the other portion of the core called the armature moves. Contact springs and armature spring. Often these contacts will be arranged so that there's a bit of wiping action. Yes, I know, I said wiping action. And the wiping action has 2 functions. The way that this is arranged as it moves in, there will be slight wiping. And so what that does is it cleans the contacts. The other advantage that we have is this is called a double make and break. And what that means is that the load current as it flows through this contact here is going to be broken at 2 places simultaneously. And that means that we lower the arcing by half by having 2 separate connections. If we had 8 connection points, we would lower it by a factor of 8. And so this is another example on a slightly different contactor of that wiping action contacts. Usually a little bit better quality than the real cheap version that I showed you here just sitting on my desk. Now remember, I said that the contactor, actually the coil inside it could possibly burn out, but that's due to this interaction of the magnetic flux and the flux path. So contactor magnetic coils can burn out due to high current if the armature is prevented from pulling in. And so this is something interesting because on a relay, this would not happen. If I jam a relay in jam the armature so that it will not move, the coil won't burn out. On a contactor, the coil will burn out. And it's kind of an interesting process as to why that is. It has to do with the inductance of the coil changing. And that's because we're physically changing the core, aren't we? So really, what ends up happening is the coil inside the current rises. When we first energize it, it rises, 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 rises. And then finally, we reach the voltage where there's enough magnetic flux that we pull the armature in right at this point here. And as soon as that happens, when the core gets pulled in, the current in the coil drops to a very low value. And it stays at about this value for the duration of the contactor being energized. If I were to block the armature, the current in the coil would continue to go up and up. And just like the current rating for a motor, the coil is only rated to handle so much current. And if I continue to see this blocked armature state where the armature is not permitted to move, the coil will burn out due to the heat inside the windings. So the reason for this is actually quite simple. We are changing the inductance from this situation to this situation over here on the right. So before the armature seals in or gets fully drawn together, the inductance in it, well, we have a long flux path. There's a long flux path, which means we have a low inductance. And if we have low inductance, remember, inductance, this formula here, that means low XL in an AC circuit and relatively high current because Z would then be quite low. As soon as the armature seals in, we have a short flux path because the armature has been drawn together and we have no air gap, right? Air is not really a fantastic permeable item for magnetic lines of flux. And this then increases the inductance, which increases the XL, the Z gets much higher, and it causes a low current. So remember, blocking the armature of a contactor, not only will it obviously prevent the armature from moving, but we could also damage the equipment. What was this thing? A shading coil. We had an image of it there, and I showed you on my contactor, a shading coil. A shading coil is something used on AC contactors. And the shading coil is actually just a metallic loop of wire, and it's embedded into the face of the coil's core. And the reason for that is purely to reduce sound. Remember, if we're using a AC power source to energize the electromagnetic coil, well, that means we have a sine wave. And the sine wave is going above zero and below zero, and we're hitting zero multiple times every second. And so what that leads to is a buzzing sound as the magnetic domains or polarities of this change 60 times a second. And so you hear this buzz, buzz like that. Now, to reduce that sound, what we do is we try to prevent the magnetic flux from reaching zero at any given point. And that's by putting this tiny little wire in. Remember, anytime there is cutting of lines of flux by a conductor, there will be an EMF generated, and therefore current would flow, and then flux would be the outcome. So the shading coil provides this teeny tiny little voltage. It should actually be shown here much lower in magnitude. But what it does is it ensures that at no point does the magnetic flux, the intensity or the strength of the flux around the coil face ever drop to zero. Because when we reach zero here on the supply voltage, the induced voltage from the shading coil is still coming down from its peak. So it's providing this small out of phase flux to make sure that we don't have this buzz, because buzzing is irritating. Let's take a look at a few different types of contactors. IEC or NEMA starters, non-latching, latching, and then finally just standard motor starters. So there's a whole bunch of different types of contactors out there. Let's look at the difference between IEC or NEMA, and I put in brackets EMAC. This is the difference between European and North American. And primarily the major difference you're going to notice here is the size. The size is substantially different. And that's because IEC, it's usually smaller, European spec, they're a little bit cheaper in price. NEMA is larger, they're considered to be bomb-proof. They're North American in their development. And so NEMA starters typically use a little bit older technology, but they're built to withstand pretty much anything. IEC starters are substantially cheaper, and they're really just intended to operate specific types of motor loads, and they're not nearly as robust, but they're extremely cheap. So you can tell that there probably is a fair number of users of IEC equipment. So the most common contactor we have is a non-latching standard contactor, and that's what I showed you the disassembly of previous. Non-latching contactor, and they come in all sorts of different variations. We have 3-pole, 2-pole, and even single-pole variants, and that's because there are different applications for each one. Perhaps you have a 240-volt motor. Well, then you don't need a 3-pole contactor, you only need a 2-pole. Of course, a 3-pole would be for a 3-phase motor, and then single pole is actually quite commonly used when it comes to HVAC equipment. And HVAC equipment will have possibly a motor that's controlled, but only one of the line connections is being opened or broken. So let's take a look at a few different variations of that. Here's a 3-pole contactor. We looked at that one already. This is a 2-pole contactor. You can see same sort of arrangement, but only 2 separate poles there, right? And then this one here is actually a single pole, and it might be hard to see, but this here is just a bar. And so there's no switching happening of this one. Over here, this is where the on-off is taking place. This is what opens and closes. And again, the whole thing has its own coil, and the coil connections are on either side of it. So single pole contactors do exist, although might not be as common in the commercial or industrial field. All right, so what else do we have? We have mechanical latching contactors, and we've looked at those already when it came to latching relays. And of course, contactors can have the same type of arrangement where the mechanical linkage is energized by 2 different separate coils. And then finally, we have a motor operation with a contactor, and in doing that, we need to have an overload relay. And the overload relay does the same function as what we looked at when we were looking at standard manual motor starters. And so the combination of the contactor with the overload block is referred to as the overload starter. The whole starter is these 2 things together. Now, just like in the standard contactors, we have 2 separate variants when it comes to the construction and what we're going to purchase. We have IEC and NEMA. So let's take a look at a real set. So here's an IEC and there's a NEMA. So this is humongous. It's like a battleship. And this is like a cute little Range Rover, right? Look at the size of that thing compared to this one. Oh my goodness. It is absolutely massive. And so this starter here is designed to operate a motor under certain conditions. And if I look at the side here, it gives me the voltage and the current rating and all the rest. Specifically, I'm going to look at how large a motor I could put on there. And it looks like I could put on a 5 horsepower, 600 volt motor. 5 horsepower. Okay. 600 volt, 3-phase. Let's look at this one here. So this one, I have the same type of information, and it looks like it can handle a little bit higher. It can handle 10 horsepower. 600 volt, 3-phase. But look at the difference in size. It is astronomical, the difference in size. And so this type of equipment is usually quite a bit more expensive than this. And really, most people will not need something that is so robust in its construction. So lots of different options available for us. Lots of different options available. All right, so we have IEC and we have NEMA equipment. Finally, let's have a brief discussion just about the different types of contactor markings and ratings that we're going to see. And the ones that you need to be concerned about as an electrician would be the coil ratings and the contact ratings. On a standard motor starter, you're going to have 2 different types of contacts. You're going to have power contacts and you're going to have control contacts. There might be 1 or multiple control contacts, but you will definitely have 3 power contacts. The coil obviously is over here. Now, very typically, the coil is marked as A1 and A2, but it really depends on the manufacturer and what type of contactor or starter we're dealing with. So the coil rating is usually printed right on the coil, and that's because the coil can be removed from the contactor. And so because of that, the coil rating is not found on the main nameplate often. Sometimes it is, but often it isn't. This one is 120 volt, 60 hertz, or 110, 50 hertz if we're overseas. This one here, the coil portion is actually right there. And so the voltage and hertz of the coil is printed right on the coil itself. And you can see the 2 terminals that would supply power to the coil. Of course, the contact ratings, the power contacts are usually what are going to be listed. So this, they're saying 3 or 5 horsepower. The control contacts very often won't have major markings on the nameplate, and that's because typically they're not handling a significant amount of current. Here again is some more information on another type of contactor. These are the contact ratings. This is also indicating the size of the contactor, and this would be a typical NEMA or EMAC sizing chart, size 1. Current value 27 amps. And then down here, they list, well, what if instead of just a straight current load, you're actually putting a motor on? And in that case, they actually list the horsepower. So we could have up to 27 amps of lighting, or we could put on these sizes of motors. So NEMA ratings are typically in the numeric values of 1, 2, 3, 00, and there are many charts that we could reference as to the required size of a NEMA starter. IEC starters, on the other hand, have their own method of identification of use. And so you see different types of ratings like AC3, AC4, AC1. And again, we would look these up in charts to determine the appropriate rating for the type of motor and the conditions of use. And that brings us to the end of our presentation on magnetic motor starters.